Okay, hey, so welcome back to our part 2. So I hope and I expect that you have gone through this paragraph. So now, in this paragraph, what we have studied is that if we change the concentration of two or if we change the concentration of any one of the side, then uh, will the electrode potential value increase or decrease. We have studied that logically or qualitatively, but right now we are going to study that quantitatively. That it's like if the electrode potential value increases or decreases, then what would be the new value of the electrode potential. Okay, so let's get started. Okay, so for that purpose, you have to know what is known as the Nernst equation. Okay, the Nernst equation. So this value, the E nu refers to a new value of electrode potential, and this is the standard electrode potential value. This value is the R, which is the universal gas constant. This value is the T. Uh, this value is T, which is the temperature in Kelvin, and this is calculated as theta plus 273. Okay, all right. Okay, and this value N is the number of electrons in the electrode equation. Now, what is this? So we will consider this later. This value F is known as the Faraday constant, which is the value of 96500 coulomb. How the value has been derived, we will talk about it later. And the value of K, this value K is known as the constant of equilibrium of the electrode potential. Now, if you do remember the value of the electrode potential, I mean the equation of the electrode potential, then let's go back to this point. Okay, so just try to remember that in an electrode potential equation, there are two sides, the right side, the left side, and the right side. The right side will always contain the reduced the reduced form of the electrolytic equation, and the left side will always contain the oxidized part or oxidized form of the electrode potential equation. Now, for simplicity, you might remember that right side contains the reduced form. All right, okay. So that means when you are going from left to right, you are doing reduction, and when you are going from right to left, then you are doing oxidation. Okay, okay. So look, now the talking about that N in the Nernst equation, that N is the number of electrons in the electrode equation. Okay, for instance, look at this equation. So in this equation, how many electrons are here? 2 electrons. So for this equation, N is equal to 2. Okay, look at this equation. In this equation, now tell me how many electrons are here? 3. So N will be equal to 3. Okay, and for this equation, N will be equal to 6. All right, okay, so that is the N. Now talking about K. So K is the, you know that I think you remember that how to write the the equilibrium constant. Equilibrium constant is written as, at the numerator you have the concentration of product, and at the denominator you have the concentration of the reactant. Okay, so here in the electrode equation, what do we have? In the electrode equation, in our product side, for example, I'm considering this equation. In the product side, we have the part which is reduced, or the right side has the reduced form and the left side has the oxidized form, or oxidation species. Okay, so we will write equilibrium constant, since the reduced part or reduced form is our product, so we will write concentration of the reduced form divided by concentration of the oxidized form. Okay, all right. Now in some cases, maybe in the right side of the equation or in the left side of the equation, you might deal with gases. Okay, you may deal with gases, but or solids, but in these cases, when you are dealing with gases or solids, take that part as 1. Okay, what do I mean to say is, like, for example, in case of this equation, oh sorry, in case of this equation, look, this is an ion, so this is an aqueous solution, so this has got a concentration, but this is a solid. Okay, so solid, that means you will consider its concentration as 1. So if you want to write the equilibrium constant for this equation, it would be like K is equal to, since this is a reduced form, but it is solid, so it should be 1 divided by concentration of copper 2 plus. All right, okay. Let's look at some more equation. Okay, then sorry. Okay, then, like, what about here? Here we have got nitrate, isn't it? So here we have got nitrate here. Okay, so here we have got nitrate and we have got NO2. All right, okay. So NO2 is a gas which will be lost actually. So we will write equilibrium constant is equal to 1 divided by concentration of nitrate. Okay, all right. So you might question that why are we taking just NO3 and NO2, why not we are taking all of them? Okay, I will answer it later, just keep it in mind. Okay, so that's how you write the Nernst equation, equilibrium constant. Now there is an issue that in some books you will find a positive sign here. Okay, you will find a positive sign here, but the equation for those books be like this, that it's equal to standard electrode potential plus RT by NF into ln 1 by K. 1 by K means concentration of the oxidized form divided by concentration of the reduced form. Okay, okay, but these two equations are actually the same, they're all the same. Okay, okay, now we have enough discussions regarding the electrode potential and something, the cell potential, what information do they give us. But now we till now we didn't had any discussion regarding how will we practically calculate the values of electrode potential and the cell potential. Now we will look at the circuit setup. Okay, so each and every circuit, the electrochemical circuits, has got two sides, one side that will gain electron and one side that will for sure lose electron. So the side that is gaining electron, we are calling it as the reduction half cell, and the side that is losing electron, we will be calling it as the oxidation half cell. Okay, so the reduction half cell and the oxidation half cell. Using the two half cells, we will prepare our electrochemical cell. Okay, now how to prepare a half cell? How to prepare a half cell? How? Okay, let's see. Look, this, the information is hidden in this portion. Okay, what does it say? Look, a half cell is set up such that it should contain everything that is present in the electrode equation. Okay, for instance, okay, so let's go back to that electrode potential values page. Okay, we will produce some electrode half cells from here. Okay, so let's go. So first look at this one. So now imagine what does it contain. Okay, so this equation contains a silver ion, electron and silver solid. So to make the silver half cell, we have to add together, we have to mix together all of these. Okay, so we are taking a beaker in which I am first taking a source of silver ion. Better for any positive charge, you better take its nitrate salt, because all nitrate salts are soluble. So for this positive silver, we are taking silver nitrate. Okay, then electron is found within metals. All right, electron is found within metal, and usually when you don't find any metal in an electrode equation, we directly use platinum. So you may prefer to use a platinum rod or a platinum wire here, but that is not actually needed. Why? I'm going to tell you. Okay, so we have a source of silver ion, we have a source of electron. Okay, now we need to fulfill the need of silver metal. Okay, so you might prefer to put small amount of silver metal at the bottom of the container. Okay, so this is the silver metal. So look, all things are present. We have source of silver ion, we have source of electron, and we have source of silver. But we can reduce our cost by eliminating the platinum. Why? Because look at the silver. Isn't silver a metal? Yes, silver is indeed a metal. So a single silver rod here in this case can satisfy the need of both silver solid and the electron source, isn't it? Let me get rid of all of this. So a single silver metal can satisfy the need of solid silver as well as the source of electron, isn't it? So our half cell may look like this, that this contains silver nitrate as a source of silver, and we are employing a silver rod which satisfies the need of silver solid, as well as the need for electron. Okay, so that's the silver half cell. Now let's go in producing the bromide half cell. the bromine half cell. Okay, so here we have a gas supply. Bromine is a liquid, isn't it? Bromine is a liquid. Okay, bromine is a liquid. Yes, I forgot. Sorry. And here we have electron. Here we have bromide ion. So no metals are present here. So as a source of electron, we must use platinum. So how would this solution look like? So this solution must contain bromine liquid mixed with, for example, potassium bromide as a source of bromide ion, all right, and then a platinum wire as a source of electron. Okay, now let's talk about chlorine. Okay, so this is important. Look here, chlorine is a gas. So how will we supply a gas? How is that even possible? But you have to make it possible by supplying chlorine gas in what we call the set of apparatus as the gas tubes. All right, gas tubes, and the gas tubes looks like this. Please draw the diagram of gas tube in your copy. A gas tube actually looks like this. Okay, and inside the gas tube there is a platinum wire. Okay, so from here inside, so from here from this terminal we supply in the gas goes in, then the gas comes out from this output terminal. So this is a gas tube. Okay, so how to set up the chlorine half cell, let me tell you. Okay, first take a beaker, okay, then let's put the source of chloride. Okay, uh, instead of making the color blue, I will make it green. So chloride ion is green. I am taking sodium chloride as the source of chloride. All right, okay, now chlorine gas. Okay, so we need a gas tube, and I'm making the red color. So what I'm doing is, okay, so this is a gas tube. Okay, this is a gas tube. So I will give chlorine from here, chlorine gas from here, and the chlorine will get out from here. Okay, now now I will give electron. This is the platinum here I'm supplying. Okay, so this platinum wire is a source of electron. So when gas is present, you must use gas tubes. Okay, now let's move on to this one, talking about this one. Okay, what are the things present already here? So we have ClO minus, we have H2O, we have Cl minus, we have OH minus. So to produce a half cell from here, we must employ all these ions. All right, okay, so let's begin. Okay, so I'm taking a beaker, and for negative ions I prefer sodium or potassium salt, and for positive ions I prefer nitrate salt. So ClO, so for ClO I am taking NaClO. All right, then H2O, so I also add some water inside it along with the solution. Then we have electron. Since no metals are present here, no metals are present all through this equation, so I have to use a platinum wire. Okay, so this is a platinum, and then I have covered something. Okay, so I have to use a platinum here. So this is a platinum. Then we have to use source of chloride. Okay, so I'm giving sodium chloride or potassium chloride. Then there is hydroxide, so I am using, for example, sodium hydroxide. Okay, so there we go. So all the things, anything, whatever things are present in the equation, you have to add it inside the half cell. Okay, that's how it works. Okay, so after you have prepared the oxidation half cell and the reduction half cell, or the two half cells, the half cells now has to be connected together, first of all electrically, then chemically. So electrically they are connected by a voltmeter, and chemically they are connected by a salt bridge. Basically this salt bridge has got two purpose: firstly to complete the circuit, and secondly to maintain the balance of charge in both the containers. Now what do you mean by the balance of charge? Okay, so balance of charge actually means, like for example, um, look, so this is a copper half cell and this is a zinc half cell. So just imagine, for instance, that copper is reduced here. All right, so copper is reduced means copper 2 plus is turned into copper, isn't it? So that means the amount of positive charge in this solution has decreased. Okay, so what will happen is that some positive ions from the salt bridge will flow into this solution and maintain the balance or the amount of positive charge. Okay, so positive ions will flow from the salt bridge into the copper half cell. Now if copper is reduced, then zinc must be oxidized, isn't it? That means zinc turns from Zn to Zn2 plus. So that means the amount of positive charge in this half cell increases, isn't it? So the amount of positive charge is increasing here. So what salt bridge would do? Salt bridge would send some negative charge into the solution to maintain or to equilibrate or to keep the amount of positive or total amount of positive charge same in the beaker of zinc. Okay, so that is the function of the salt bridge. Number one, to complete the circuit, and number two, to maintain the balance of the charge in both the half cells. Okay, so how is a salt bridge made? Okay, a salt bridge is very simple. Take a tissue paper or take a filter paper or take a very good soaking cloth. So what and then um, soak it inside a solution which contains ionic compound, which may be sodium nitrate or which may be potassium nitrate. I prefer these two solutions because these two solutions are soluble, and they are quite unreactive also. You can also take any other solutions, but they might react with the components of the half cells. So I always prefer sodium nitrate or potassium nitrate. Okay. Okay. Ammonium nitrate is also a good option. You might argue that, sir, if I use sodium chloride, okay, you can use, no problem. But if any of the half cell is made up of silver, then that chloride might form a precipitate with that silver. Okay. Okay. Look, some examples of half cells are given here. Okay, I think I should talk about positive electrode and negative electrode. Okay, so let's go to the case of copper. Look, here I have told a few moments ago that copper will be reduced. Reduced means the copper side is gaining electron, isn't it? So electron is being gained. So which charge attracts electrons? Positive charge, isn't it? So think like that, that copper electrode is gaining electrons, which means we can think it as a positive charged rod which is attracting electrons. So that's why the half cell or the side which gets reduced is the positive electrode. Okay, and the side which is oxidized, that means which loses the electron, it seems like that, it seems or it appears to be like that. This rod is negative, so it's repelling the electrons away from it. Okay, that's why the rod which loses the electrons is considered as the negative electrode. Okay. Okay, so electrons flow. Cambridge may sometimes ask you about the flow of electrons. So electrons always flow to the side which gets what? Reduced. Okay, so electrons will flow to this side. Okay, now for instance, so this is MnO4 Mn2 plus half cell, and this is hydrogen half cell. So let's see the values. MnO4 Mn2 plus. Okay, so the value, so this is present over here, so its value is 1.52, isn't it? Value is 1.52. And talking about hydrogen, the electrode potential value of hydrogen is 0. So MnO4 minus Mn2 plus half cell is more positive, isn't it? Sorry. So that half cell is more positive, isn't it? So that means what would happen? So so this side of the half cell is has got a more positive electrode potential value. So what would happen is that this side would gain electron, and that means oxidize, and this side would lose electron. Okay, so electrons would flow from this side to that side. So you know that electric current flow is the opposite of electron flow, isn't it? So if electrons flow in this direction, then electric current would flow in that direction. And you know from physics that electric current always flows from the positive terminal to the negative terminal. Okay, so that's why this terminal is considered as positive and this terminal is considered as negative. But you might also think the positive and negative terminal in the way just I have told a few moments ago, that this side is gaining electron. So since it's gaining electron, that means it has got lack of electron, that means it is positive. And this side has got excess of electron, so it is losing electron. So this side is considered to be negative. Or you can also consider the electric current analogy. Okay. Okay, so that's the fact I'm telling. Now okay, so that's the end of the part of electrochemical cells. Now let's go to electrolysis. So electrolysis has got what happens is that already have studied from your O levels that during electrolysis the charged particles are neutralized, isn't it? The charged particles get neutralized. That means the negative charges, they lose their electron to become neutral, and positive charges, they gain electron to become neutral. Okay, so positive charges are reduced and negative charges are oxidized to become neutral. Now from the electrode potential value, you can easily predict that who is going to get oxidized and who is going to get reduced. Okay, who is going to get oxidized? Just think it in this way, that when two systems are present, like system of A and system of B, like you have to oxidize any one of them. Okay, so who is going to get oxidized? Suppose A has an electrode potential value of +1, B has an electric potential value of +2. So which system is going to get oxidized? Okay, the system which has a lower tendency of getting of becoming or getting reduced, the lower tendency of getting reduced must have a higher tendency of getting oxidized, isn't it? So here the value is +1, here the value is +2. So the value +1 is a higher value, and the value of +1 is a lower value, and +2 is a higher value. So this value +2 means this is a higher value. So the system of B has a higher tendency of getting reduced. So the system of A has have a higher tendency of getting oxidized. So if there is a question of oxidation, then A will be oxidized. Okay, consider it in this way. Okay, for example, if I tell you that from among the solutions, solution contains silver nitrate. No, a solution contains silver chloride and calcium bromide. Okay, and calcium bromide. So if we carry out the electrolysis of this solution, then which is going to get oxidized and which is going to get reduced?